Math 3 Lesson Summary Video Centers of a Triangle. This lesson is a practice understanding task, which takes concepts you have been working on and applies them to new situations. The purpose of this lesson is to practice thinking through and contributing to the reasoning of a property for a familiar shape. Before you can do this task, you do want to go back and make sure you review some vocabulary from Math 2. There were some segments that we've dealt with that we constructed, and we want to make sure we remember how to use them and what they are. In a triangle, if you connect the vertex to the midpoint of the opposite side, this segment is called a median. If you find the segment that goes through the midpoint and is perpendicular to a side of a triangle, that is a perpendicular bisector. If you have a segment that cuts an angle in half into two equal angles, this is called an angle bisector. And if you connect the vertex of a triangle to the opposite side perpendicular at a 90-degree angle, that is called the altitude. You may have also called it the height. In problem 1, Colton's father has installed a sprinkler system for the farmers, and the system he installed is called the center pivot irrigation system, since the sprinklers are on a long pipe that rotates around on wheels around a center point, watering a circular region of the crops. You may have seen such crop circles from an airplane. Sometimes Colton's father has to install sprinkler systems on triangular-shaped pieces of land. He wants to be able to locate the pivot point in the triangular field so that the circle being watered will touch each of the three fences that form the boundaries of the field. He has asked for Colton's help with the problem since Colton is currently studying geometry in high school. So if this is his triangular field, we are looking for some point that he'll be able to put the center of the irrigation system, and it will go along and it'll just scrape up against the fence. So he's gotten as much of that triangular field as possible with this circular thing. He can't go outside of the fence, the pipe. He doesn't want to knock the fence down, but he does want to stay inside of it. So we just need to think about some of our tools that we have in our toolbox that maybe we could use to help us find this. We just went over there are several types of segments you can do in a triangle. 3 of them went through a vertex. A couple of them go through a midpoint. So these are kind of things that we want to be watching out for to see if we can find it. If we're looking for one single point, we're probably going to be looking for a place where segments intersect. That's kind of a common tool. If you think about how we found the center of rotation for our parallelograms, we looked for where the diagonals intersected. So many times, if we're looking for one particular point, you're looking for where something intersects. It's a good tool to kind of fall back on. So I just want to start drawing some segments to see if any of my segments intersect at that one point. I'm just going to start real basic, and I'm going to try connecting the vertex to that point. My line is not terribly straight. I would hope you guys would use a ruler. All right, so if I draw from the vertex to the point, I kind of get these lines, and I'm trying to look and see. I don't think it's going through the midpoint because this piece is visibly shorter than this piece. So I don't think it's a median. It's not perpendicular. That's definitely not even close to being a 90-degree angle. So I don't think it's an altitude or a perpendicular bisector. But I do notice these angles aren't too terribly off. This one was not drawn the best, but they definitely look like they could be cut in half. So I think it is safe for us to say that we're dealing with angle bisectors. If we want to find this point that's going to go brush right up against the fence post, we're looking for where the angle bisectors intersect. These segments are concurrent. Here's a vocabulary word for you. They're concurrent. that means they all three intersect at one point. Two lines intersecting at a point, that's not unusual. All lines that are not parallel intersect at a point. But for 3 lines to intersect at one point is a slightly bigger deal. And so we call that being concurrent. So these 3 segments in a triangle are always concurrent. And in fact, we call this point the incenter of a circle. That makes sense. It's inside the circle, and it's inside the triangle, and it creates a circle. The whole circle stays inside the triangle, so it is in the center. It is important to note that it is tangent. The circle is tangent to the triangle, so each of the sides of the triangle end up being tangent to the circle. We call this being inscribed into the triangle. So the circle is inscribed in the triangle, and it is called the incenter, and we find it by the angle bisectors. For problem number 2, Kara's father installs cell towers. Since phone signals bounce from tower to tower, they have to be carefully located. Sometimes Kara's father needs to locate a new tower so that it is equidistant from 3 existing towers. He thinks of the 3 towers that are already in place as the vertices of a triangle, and he needs to be able to find a point that is in the center of the triangle where he might locate the new tower so that it is equidistant from the other 3. So we want this distance, the distance from the 3 towers, to be the same. And so as you can see in the picture, if we think about points that are the same distance from another point, remember, that's what the definition of a circle is. A circle is all of the points that are equidistant. So what we're really looking for is the center of a circle that goes through all 3 vertices. That would make the vertice to that point be a radius. So we're looking for this circle. Now we do have a term for this type of circle. This circle goes through all 3 vertices and is not tangent, and we call this a circumscribed circle because it goes around the polygon and touches all of the vertices, so it is circumscribed. And we want to know, where is this point? So this is where, again, I just start looking for things. I can tell if I were to connect this point and that point, it is not going to be going to any midpoint. It is not going to be perpendicular, and it is not even close to cutting that angle in half. So that kind of gets rid of some of my options. I do want to look at midpoints. Where are the midpoints? If I go from here to here, it's definitely not going to the midpoints, but when I look for the midpoints of each side, it looks like one's about right here. Maybe we've got one about right here. And this one's halfway point, probably about here, if we were looking for midpoints. If I were to connect that point to each of those midpoints, one thing I notice is if it goes through the midpoints, that is pretty close to looking like an exact 90-degree angle. And in fact, it is. So if you look at it, it's 90 degrees, it's perpendicular, and it goes through the midpoint. That makes these perpendicular bisectors. And so it looks like we are looking for, where are the perpendicular bisectors concurrent? Where are they all 3 going to intersect? And when they intersect, that gives us the point that is equidistant from all of them. And again, we do say that it makes a circumscribed circle, so it makes sense that the name of this point is called the circumcenter of the triangle. So it is the circumcenter of the triangle because it creates a circumscribed circle about the triangle. And our last problem, Kevin's father is an artist and has been commissioned by the city to build an art project in the park. His proposal consists of several large pyramids with different shaped triangles balanced on the vertex point of the pyramids. Kevin's father needs to be able to find a point inside of the triangle that he calls the balancing point. In science class, we may have thought of it as the center of gravity. he has asked Kevin to use his knowledge of geometry to help him with this problem. So again, all of these have been centers, some kind of definition of a center inside the middle of a triangle somewhere. This one we want to be where we really balance the weight, that center of gravity where we can actually balance the weight of this shape. And so again, we're looking for some kind of pattern or connection for these concurrent segments. Now, they've already drawn a line here from the vertex because, we're dealing with a pyramid. So these are kind of the edges of the pyramid, but it also gives me a visual in the triangle. If I were to just continue that line on, it would be around here somewhere. And that, it looks like it might be in the middle. If I were to continue this line on, it's pretty darn close to the middle as well. And so again, if I'm just eyeballing it, oh, that looks like it's also in the middle. So this is connecting a vertex to a midpoint, and we said that we called those points the medians. So if you find where the medians are all concurrent, where they all intersect, this is going to give you the center of a triangle that is basically its center of gravity, and we call that point the centroid. Now, a centroid does not necessarily give us the exact center of a circle. Like, we're not making a circle that's inscribed or a circle that's circumscribed. In fact, it's about taking a balance and a weight of the triangle so that it's all going off equally in all three directions. And so what it really does create is it creates a proportion. In fact, this centroid, the point where they intersect, creates a proportion between all three of these segments. Where they intersect breaks each segment into 3 equal pieces. 2 of the pieces are on the vertex side, and 1 of the pieces is opposite of the vertex. So you're basically making a 2-to-1 ratio for all of these pieces. And so you end up with these pieces that weight-wise are balanced out. You get that perfect proportion.